Okay. Good day, everyone. Thank you, Marcel and Si2 OpenAccess Coalition for this opportunity. I am Rakkesh Kumar here, co-founder and chief product officer at Maieutic Semiconductors, where we are building an AI-driven co-pilot for analog chip design. So, first question maybe coming into everyone's mind: what is Maieutic stands for? It's a Socratic method of learning through questioning. I'll not go more detail because we have limited time. So today's talk is about going beyond parametric tuning or the optimization using generative AI assistants, which helps designer actually pick and modify circuit topology, not just size them. The problem with today's analog automation. So analog design automation, if you see, it has been stuck on parametric optimization for decades. The optimizer tunes like width, length, bias current, capacitor values, or register trims. But fundamentally, it can't change what the input circuit topology is given or the architecture. The topology is treated as a constant, chosen by human upfront and never revisited by the tool. So that means it only given a limited range to optimize the circuit. This means the optimizer gets trapped in a local neighborhood, or in best case, it can get the best possible result for a given topology or the architecture. If the selected topology is not the right one for a given performance or the target, no amount of sizing is going to fix it. Coming to the next or the technology node and the supply voltage, as the technology is shrinking, the supply voltage is reducing. This makes the topology choice matters more than what it was earlier. So the main takeaway from this slide is that topology is treated as a constant, which is not the right way to approach a design. So what's the Maieutic approach? So Maieutic approach is fundamentally a designer in loop framework where the AI assists, but the designer remains the full decision maker. So here I have shown 3 points. The first one is the starting point. We don't force a blank slate. The designer can bring an existing design or a new design they have drafted, or it can also be AI assisted design creation. In step 2, which is the critical point highlighted here, is the topology selection. So now, based on the schematic simulation of the starting design, the designer chooses how to proceed in one of the two modes given here. Mode A, where the AI suggests candidate topology modification, designer picks the one to pursue. In mode B, the designer specifies exactly which topology element to modify and how, and the AI helps executing the change. Now the step 3, once the topology is selected, the standard sizing happens within the given topology. The key takeaway here is this is a step function departure from parametric only flow and still keeping the designer in control. I want to highlight a few key technical challenges and how we are addressing them. Now, first set of challenge is the training data scarcity. Verified PVT clean topology performance pairs are limited, and most are locked inside a proprietary IP or the design, or sometimes the design and the simulation data are not together. Only we have the final like design review kind of slides. So how do we address it? We address by basically generating synthetic data and using the result of the synthetic data and plus the reinforcement learning. Coming to the next PDK awareness. So now any topology generated have to be manufactured in a real PDK. So how we address this? We pass structured device information like a for a given device in a given technology, let's say GF or TSMC, 28 nanometer or 22 nanometer. We give information for a specific transistor, how to use it, that additional information has to be given, and that too in a structured format, along with additional data like connectivity, design rules, etc. is passed as a context to the AI. So the AI understand how to use that particular component. Now, the third item here is the simulation in the loop. Full spice for every candidate is too slow. What we use is a specific topology model for faster loop conversions, and then we do selective full spice validation. So this reduces the overall simulation time and helps in converging it faster. Coming to the PVT coverage, this is also a very time consuming simulation and phase, and sweeping all corner on every iteration will take a lot of time. So what we do, we use a ML based worst corner prediction so that we can selectively run on those corner first and make the design robust, and then of course at the end we can fire run for all the corner and get the result. This is the role of Si2 and OpenAccess. So Si2 has done a great work in making OA format as a common interface, and this helps a lot of companies get started fast with the in the ecosystem. Generative AI outputs are only as useful as their ability to be integrated or shared across different tools. At Maieutic, our roadmap targets seamless OA-based data exchange across the OA conformant tool ecosystem. One point I would like to highlight here, which is related to the CDF callback. This is the one of the issue right now I would like to highlight. CDF callbacks are vendor specific. Cadence and skill-based callbacks tied to Virtuoso. Synopsys has a separate proprietary callback model in custom compiler. Any AI tool that wants to drive topology automation has to re-implement against each vendor, depending upon the PDK and the tool, or pick one and then it gets locked to that. So what we are seeking is a standardized callback interface as part of the OA spec, like write once, run across OA compliant tool, and solving it would unblock AI-driven topology automation at a ecosystem scale. Okay, coming to this is basically demonstrating the Maieutic capability. And I would like to walk you all through an actual session in our tool on a differential amplifier, which circuit snapshot is shown here. This flow has like three phase. You can see the analyze phase, which is like existing bias condition can be analyzed, modify the topology, which is the second phase, and third is the optimization. Anytime the circuit meets the target, we can get to the output stage. Otherwise, we go to the iteration loop and again starts the analysis or the next phase topology and optimization. So next slides, few slides, I'll show the real screenshot of the tool, which has gone through these three steps. First one is the analysis of the bias margin. Here the designer starts with a high level natural language instruction. You can see it is highlighted in the blue. Simulate and verify bias margin of all transistor and tabulate the one with the issues. This is the natural language English instruction has been given. The AI understands it, runs the simulation, parses result, and tabulates translator with a marginal transistor with a marginal bias. You can see VGS, VDS, VT, and headroom for each. This is highlighted in the green section, structured table. And the designer again asks what are the suggested possible fix, and it goes further and analyzes the circuit and log with the simulation data and identifies a root cause for the bias issue. And you can see in this highlighted green section, it offers next step to the designer. Now, designer has a choice, either he can make the fix himself and ask the AI to run the simulation or the analysis, or you can see there is a option provided, make the bias adjustment directly and AI will execute that task. So here we have shown on this slide that the bias margin analyzed and the AI has suggested the next possible fix in that. Here we'll see the example of topology modification. So here the designer issue a high level command similar to the previous slide it's shown, like a revert to Ahuja compensation, resimulate and report the result. which is shown here in the blue section. The AI reasons through the steps and understand what has to be done and starts like removing existing Miller compensation components, which was already present in the present state. And then it adds the Miller Ahuja related capacitor back. And here you can see in the green section highlighted the exact steps taken to achieve that. So if I go to the next slide where it has completed those steps, you can see the schematic has been modified. The Miller RC has been removed and it has been replaced with the Ahuja capacitor at the right nodes connection. And all the schematic changes are persisted to the OA database. This is where the OA format data exchange matters. After modification, the designer asked the AI to compare the two topologies. Correct. So it already had the previous result for the Miller, and after reverting to Ahuja, it has done the analysis on the. So both the simulation and produce the structure comparison. You can see here is the structure highlighted in the green, and here the comparison is the DC gain, gain bandwidth, phase margin, 3 dB frequency, and compensation components are highlighted here. So what we can see, the key result is the AUSA delivers higher gain bandwidth with the simpler topology, single component versus two components. And this is exactly the kind of side-by-side comparison that used to take hours or maybe days of manual setup. Here it's a single conversation in a few minutes. Moving to the next phase, which is the optimization example. So once the topology is settled in the previous, the designer asks for help with the sizing optimization. For example, designer asks which algorithm is good to use as a circuit sizing optimizer. So to highlight here, there is not a fixed optimizer inside the tool used. This is on the fly, which is suggested by the AI tool. So then AI recommends approaches suited for the analog problem. So you can see the two optimization algorithm is suggested. One is the differential evolution and Bayesian optimization. So after getting this input, the designer in the next step ask, take a build a Bayesian optimization program and give a target of 60 degree as a phase margin. So the algorithm is given and the target is also given. And the AI sets up the selected algo for optimization, runs it, and the right side you can see the result. It has achieved the target by exceeding 2.3 degree. So eventually it meets the target and it has shown how the selected algorithm used and achieved the target. And here also you can see the Gaussian process prediction match the actual simulation result. So you can see the full flow, analyze, modify, and optimize has been shown in the three phases. Coming to the last slide, and to summarize, the generative AI can do much more than parametric tuning. It can help designer analyze, modify, and optimize topology in a single conversational flow. We also highlighted and asked to consider standardizing CDF callback as part of the OA. And thank you, everyone. And I would be happy to take questions. You can also find us at maieutic or contact us directly at the email shown below.